linear versus nonlinear systems. So this is the part where we come to things like saturation. What is P1? What is saturation? What is OIP3? Those type of specifications that we had in the very first assessment, remember? So we had specs around P1, we had something around OIP3. So those things are, like, we are trying to understand what they mean as part of this lecture, okay? So ideally, you'll have linear and nonlinear systems. Most of the systems are nonlinear when it comes to electronics. So linear system, you'd expect whatever the input you give. So for example, in here you have X1, then if it's an amplifier, it gives you Y1 output, like say at a particular frequency, right? And then other X2 output, it will give you Y2 output. So when you combine your inputs, and then your output would be Y1 plus Y2, that's a linear system. But our nonlinear system will have Y1 plus Y2 plus some additional terms, right? So additional terms are unwanted signals, but you can't do much because the nonlinearity within the system creates them. Okay, so you have to deal, or you have to work around them when you design your systems. So, for example, if you have a linear amplification, now you can, for example, you have your low noise amplifier that you guys design. The input can be low power, and then you have a certain amplification, you'll get an output, right? But, so say you F1, F2 is two different frequencies here. So you have, so we are talking about like just pulse signals, right? So if you have a signal with a certain power level, so F1 at F1 frequency, so the height of this is the amplitude, and that represents the power that the signal carry. Now F2 is another signal that has lower power, but when you combine them, they both get amplified through the amplifier. In a linear system, you'll just have F1, F2, same two frequencies, much amplified signal. The difference corresponds to the gain that the amplifier gives you, right? In a nonlinear system, you will have, say, F1, F2. So you'll have amplified signals as F1, F2. So the figure on the left here, they should be actually similar to this. Then you have amplified signals, and then you will also have some additional signals that appear outside the band. That's due to nonlinearity. Any questions?
Those are the signals like the amplifier creates?
Amplifier creates. So this, at the input of the amplifier, you just have these two pulses, just for explanation purposes. You don't have anything else, but out of the amplifier, you'll have some additional stuff, right? So that's due to nonlinearity. Now this can be due to the way that transistors are made, right? So you can't really get away, you can't really not have them, pretty much. Now these things become very dominant when you work at high power input levels. Now if you are receiving at a very low power input level, you might not notice them because they are very low in power. We'll come to that in the next couple of slides. Especially if you are working on a high power amplifier, you will be pretty much working at the highest power level that's possible. Then you will start to notice your main wanted signals plus the unwanted signals appearing. So at low input levels, you can actually assume they are linear, but high input levels, for example, in power amplifiers, you will have these additional extra signals appearing. So the same way, nonlinearity will produce you harmonics as well. So you will have your harmonic, plus then you have a harmonic distortion, right? So for example, so to get a physical sense of this, say you have 50 hertz DC to DC converter, right? So you have a 50 hertz main signal, then your harmonic would be 100, 150, 200, 250 likewise, right? So there'll be a harmonic of that at say 2.4 gigahertz. Or that's probably 100th harmonic, you don't know, right? but that is very low level. It doesn't really impact your, say 2.4 is your Wi-Fi, right? It doesn't impact your Wi-Fi. But if you have a very high power DC to DC converter for some reason, ideally, then it will have your harmonics tend to actually lower. As when you go at higher harmonics, your power level is very low, and you don't really notice them because they are pretty much inside your noise level. But if this amplitude level is too high, your harmonics are also high, then you can notice them, right? Especially your first harmonic, second harmonic will be high values. So if you have a not a microwave, something working on, like say your GSM signals that works around 1.2, if you have high power amplifier there, it could actually produce a harmonic that overlaps in 2.4. That can cause interference to other systems, right? So you want to minimize this level of the amplitude of the harmonics. That's due to nonlinearity in the amplifier that these are caused. So one thing that we want to characterize a system. So when you very first time when you did your lab, you never had an idea about how you're going to design this amplifier, right? Like LNA at all. But you know it's a block. But the block has some specs. That's it. You know. So for anyone else who's not a designer, doesn't need to know what is inside. You just give them some specs. One of the specs that you give them is P1 dB, right? So even if you get a totally unfamiliar circuit, but if you know the P1 dB, you sort of get an idea, okay, this is the limit. You can't go beyond that. Now, so one measure that you actually provide is P1 dB. Now I'll try to explain it as simple as I can. So this is your input power, this is your output power. So for the given input, you have an output power level, right? So that means this gradient will give you your gain, right? Is that right? P out over P in, right? But this is in dBm, so it won't give you a gain. Okay, so in this case it won't. So these little things would be useful for you because in the exams there will be questions around this. Okay, so make sure if it's in dB, this axis. If this axis was not in dB, if it's voltage, out divided by in is your gain, voltage gain. This is in dB. So this one, maybe I should. So if this axis was V in, V out, that gradient is your voltage gain. Okay, but in this case, if you actually have the P out, P in, not in dBs, just in watts, P out over P in will be your gain, right? But not the dB gain, just the gain, numerical gain. Now this is in dBs. What happens is your gain is P out over P in. So when you get log of that, P out. So in a log, this is a dB. That's dB. So basically, this at the value here is your gain. Now this is not the right graph. Obviously, you would need to have something like that, and that value that you read here would be your gain. Okay. Okay. Now that's for this graph. It's not really very important, but what you will notice for this input, you will have your particular output power, and so if you write this, if you rearrange this log P out, I would say just P out dB equals log P in dB plus the gain, right? If I just rearrange this, because this is P in dB and that's P out dB and that's just the gain. Now that's positive, and then you will notice that this is equal to y equals mx plus c sort of rotation, right? And then your gradient is 1. So this gradient is always 1 in a log scale. So what happens, you would expect then with the P in increase this way, your P out will increase, but at up to a certain limit only. After that, the P out doesn't linearly increase, they tend to slow down. And a point where your P out is 1 dB lower than your linearly increased P out is called the P1 dB, right? So at that P1 dB output power, that means you're operating in your maximum input power pretty much. Because you can, that means at this point, you expect it to give you this much, this level, but it can't give you, it can't drive that much power. It just gives you P1 dB, it gives you lower power than you anticipate, right? So you don't really want to operate in that range, because if you operate at a higher power input, you will always get less power than you desire, right? So this pretty much sets your upper limit in your output power, P1 dB, and then you tend to work at a lower power level. For LNAs, you work at lower power levels around here. But for power amplifiers, you guys work out higher power levels here. Now anyway, so that's what P1 dB is. This is just a common measure. Now you can't really simulate P1 dB easily because you don't know. There's a way to simulate that, but in your exercise we won't really cover that up. Yeah.
So let's say I'm comparing two amplifiers, and one has higher P1 dB than the other. So that means that is better?
It's better in terms of the output power it can handle, but is it better in terms of gain? We have to compare other specs. Yeah. So you can have another amplifier that has a lower gain but has a higher P1 dB. It depends on your application whether you're happy with it, right?
So if I need higher output power, I would prefer P1 dB to be higher if I'm looking for.
Yes, obviously. Your P1 dB has to be higher. So in your assessment, what's the P1 dB? Is it 13 dBm or something? Yeah, right. So, and I've shown you how to actually PSAT, it's called PSAT as well, to plot it, right, in the exercise. Okay, so this is, so we call it transistor goes to distortion when it deviates from its linear range. So P1 dB, at P1 dB, obviously it's actually deviated from its linear range. So that's a nonlinear measure actually. So it's in distortion. We call this amplitude to amplitude distortion, or you can have amplitude to phase distortion. You guys haven't really dealt with that because it wasn't very important for LNA. That means with the input power, you can also look at the phase of the output. Things like phase shifters will actually look at phase. They don't really worry about the amplitude of the output, right? So for them, when you work at different power ranges, you'll need to make sure your phase doesn't change. See, this phase is constant, irrespective of your power input level. But if it starts dropping at a certain power level, the amplifier is not, the phase shifter is not useful anymore. So that depending on other applications, so you can have phase distortion as well. I've sort of discussed this when we were talking. So this is again what I've derived before. So you have P out, which is the y-axis. Your P in is your x-axis, and that's your gain. So gain is pretty much, if you want to find out the gain on a P in P out graph, the power in power out graph, this y-axis where the P in curve intersect is your gain, right? And then it goes linearly, and then it tends to deviate, and that will be your, when it drops 1 dB from the linear region, and this reading is your P1 dB. So if you are given a graph to read off P1 dB, you should know like how to read it off. It's quite simple, or you can actually, you probably should remember how to draw this graph as well, right, for given numbers. So that's a measure of the transistor going to nonlinear region. Now the other thing that we should also put more emphasis on is intermodulation. Now in intermodulation, so when I talked about that before, this 1 dB compression point is mainly about your output having a lower power than what you want, right? It's not about causing extra signals. So this is two different things. Input, when you have input, you have an output, but output is not what you expect. It's lower than what you wanted, and that's a P1 dB when it's in saturation. This is the second aspect of it. So you can have saturation, the linear distortion, and then you can have intermodulation. Something called intermodulation is pretty much you give an input signal, you expect an output. That output is there, plus you have some additional stuff. You get bonus, which is not, although it's bonus, it's not what you want. So in a real time domain, if you look at a two-tone input waveform shown here, if you have distortion, if you have intermodulation, what happens is you tend to actually clip the edges. Now it's very hard to analyze signals in time domain because it doesn't give you much information. So you tend to look at them in your frequency domain, right? So when you look at the frequency domain, what happens is this is the two expected signals, and then you have some additional signals appearing on the two sides. They don't only appear here, they will have multiple of them, okay? And these are called the intermodulation products. Now, this is where it gets this very interesting and important to remember. So the two tones that appear next to the main signal, we call them third order intermodulation product. Okay? So that's the reason why they call these are called third order IMD. Okay? Now, so there's a way you can calculate what frequency is actually you can expect an intermodulation product. So if you have pulses F1, F2, so this F4 will be 2F1 minus F2. Sorry, 2F2 minus F1. And this would be 2F1 minus F2. So for example, say this is 100 megahertz and this 120 megahertz. Okay? And if you are asked to find out the intermodulation frequencies, third order intermodulation frequencies, you just need to, this frequency would be 2 times 120 minus 100, which is 2 times 120, 240 minus 100, 140. So this is 140. This is 2 times 100 minus 120, 200, that's 80. Okay? So you need to be able to calculate the third order intermodulation product frequencies. So see, the gap is only 20 megahertz, right? And that's the gap between the two main pulse signals. So if you have a system that has only one pulse, can it create intermodulation product? No, it can't pretty much, right? Because it has only one signal. But in reality, you will have a certain bandwidth, right? The reason I took two pulse signals, in reality you will have a bandwidth, which means within that bandwidth you have signals, right? So them itself, let's say it could be 1 megahertz apart, but they can itself actually cause you intermode, right? So this is just So ideally when it happens, you have wideband signal. If you have wideband signal, you can have multiple intermodulation products. And what you see in real life, this is a digital modulator signal at the input of the nonlinear amplifier. This is actually a frequency domain. Your output, you expect the same signal, because if your amplifier only works for that band, you expect that to be high power, right? And this to be not much amplified, right? But you will notice, although it doesn't really amplify this part, your intermodes caused by the carriers here will actually have lift your sidebands, right? So if you have two signals, for example, OFDM or MIMO, of the OFDM, so you have, so whatever your band, you have a chunk of spectrum, say bandwidth 1, you have signals. And that two signals can mix and appear in the next adjacent band. So intermodulation is a problem for adjacent band, right? So you need to make sure the power level of that is actually lower than the main carrier. So there's a carrier already, and because of this signal, this signal becomes the noise flow for a signal. So you can only detect this much, right? So intermodulation in that sense is not desirable at all, right? So you pretty much don't want your intermodulation. Now the spec that you have is something called IP3. And then I used terms interchangeably, OIP3 and IIP3 previously, right? Maybe that didn't make much sense at the time for you guys. So the thing that we're after is IP3. IP3 is the third order intermodulation product, which is called, so we write it IP3. That's the third order IMD. Now, why do I say third order? In here, that's 2 and that's 1, right? Coefficient 2 and coefficient 1, right? So 2 plus 1 is 3. That's why it's third order intermodulation product. Now, you can have other intermodulation products. So if you look at 2F1 is just the harmonic, right? Right? So its harmonic will appear somewhere else, and the second harmonic will appear somewhere else. And those harmonics, so this is 2F1 minus F2 will cause you this F4. So you could have 3F1 minus 2F2. So this is a fifth order intermodulation product, right? You could have, so when you do the max, you'll find only odd numbers creates your intermodulation products. So you will have a third order intermodulation product, you will have fifth order, you have seventh order, you have ninth order. Likewise, your intermodulation products will actually spread. But the one that is with the highest amplitudes is your third order intermodulation product. Okay, is that clear so far? Okay. Now this actually shows you, this graph shows you two main carrier signals and the intermodulation products. This is third order. Then you have the fifth order, then you have seventh order. We don't care about fifth and seventh order because two third orders is the most, we care about fifth and seventh order, not that we don't care. It's just like they don't really happen to be adjacent to your channel. But if the fifth order is high enough, it can cause interference. Okay, so this is very important for your exam, this part. So I think you should also read more things about OIP3, IIP3. Now I'm going to build up this one on the this graph on the left. I'll go step by step. Now theoretically we can calculate the power level of the intermodulation product. That means, so that's your two carriers. You can calculate what's the power level of this one. Okay. So if you are not clear on any of these terms, just ask me, stop me and ask me. So your P in and P out. So for example, let's say I'll go with the numbers because it's easy to remember. You don't have to remember this, any of these, because you can actually make it out from the graph itself. If you want, you can remember. There will be a question in the exam using on the third order intermodes, right? So that question involves, I'm going to do a similar question, which is our next slide. But I want to, so you need to understand this pretty much the curves here. So say you have a 20 dB amplifier. Now that means whatever your input power plus 20 dB would be your output power, right? So that means at Pin equals 0 dBm, and this is 20, your output would be 20 dBm. Is that clear? So if you are here at 5 dBm, what is your output? 25. Okay, so that's very easy. So that's pretty much this equation, right? So you don't need to remember it in terms of equation. As long as you know it using the graph, that's enough. Okay, so this graph pretty much gives you the output power for a given input power, right? Once you know the gain, right? So if it's in the linear region, it will follow this line. Okay, clear so far? Now what happens is after a certain input power, because your input power increases, right? What is the gradient of this? 1. Okay, so that's gradient 1. Question? Okay. Now after a certain level, you tend to see your third order intermodulation products coming above the noise floor, because initially you won't notice them because they are below your noise floors and it's adjacent channel anyway, but then they tend to creep up. Say for example at a particular point input power, so this axis now, on this axis you are measuring pretty much output signal. This is your desired signal power level. Then you tend to actually see at a certain power input, because your power input is higher, you have another signal which is on the, so this is your input, and you have an output, this is your two inputs, you have two outputs, then you tend to see this creeping up. And that power level initially is lower, because this level is lower than that, starting here, and then as you increase your input power, this tends to go up, right? But they tend to go up faster than your desired signal output. Okay, so that's a measured plus the theoretically derived formula, but you don't need to know how to derive it. It's just that you need to know it. They tend to go up in the gradient of 3. So which means for each 1 dB step of input, your output goes 1 dB up because it has a gradient 1. But your IMD grows 3 dBs. So the difference is 2 dB. So it's catching up, right? So there will be a point where your IMD levels is same as your output levels, right? And that point we call the IP3 point. Now if you measure the output power at that level, if you measure the output power, we call that OIP3. Okay, so in your spec, I think it was 36 or something. Oh, what was it? I can't remember. In the assessment. Maybe it's 16 or something. Yeah, okay. So that means at 16 dBm, right? At 16 dBm output, your your IMD levels and your output level is equal power levels. Now, if you look at the input power level, where you have the IMDs and the output same, we call that your IIP3, input IP3. Now, okay, so for example, if you have, say my input IIP3 is 10 dBm. What is my output OIP3? Sorry? 30. Because that, for that, so just treat it as a power input level. And then because it just has to have a 20 dB gain, if it's 20 dB gain, this is 30 dBm, right? Right? That's 30 dBm. So now the questions that you, so that's what this curve's about. So the IIP3 plus G, which is 20 plus 10 gives you 30. This is pretty much saying 10, that's 20, and that's X, right? That's what you did. X equals 10 plus 20, which is 30. So you don't really need to use the equation, you can just work it out from the graph. Now the questions, you can form the questions in such a way that, so what is your IMD at, say, 7 dBm? How do you work that out? Any guesses? Okay, so I'm going to do it slowly. Okay, so at 10 dBm, you are 30 dBm out, right? That is output power plus your IMD power, 30 dBm. Now at 7 dBm, you are, what? How many points are you there here? You are 10 plus 7, that's 3, right? Got it? And that's gradient of 3. So this has to be 9, right? You know this is 30, so this level has to be 30 minus 9, which is 21 dBm. Is that clear? So basically at 7 dBm, you will have your IMD 21 dBm. Your output will be 7 plus 20, 27 dBm. Is that clear? And then as you move forward, it tends to catch up. And then at 30 dBm, it catches up. Okay? So basically it's, so if you have a question, we will do this example, I think that's more useful. Okay, so an amplifier has a linear gain of, I think I probably have done that anyway, but we'll do it again. 20 dB. OIP3 of, or at least the OIP3 is different, 33 dBm. Find IIP3. So what would be your IIP3? So it's quite straightforward, right? So you have that 33 dBm, and that should be 33 minus 20, that's 13 dBm. So find P out at P in 10 dBm. So at P in 10 dBm, which is here, what is your P out? 30. Why is that? Because 10 plus gain, right? That's 30. So it's easy as long as you know what you're looking for, right? If you know what your terms are, right? So the exam's not that hard. It's just that you need to know what you are pretty much So we did that, that's 30. Then find IM3 power level at P in 10 dBm. What is your IM3? You guys want to try it first? So the IM3 curve will go like that, right? So IM3 curve will meet the P out curve at 33 dBm, right? So they're asking at P in 10 dBm here, which is 3 gap, what is your IM3? So it's very similar to what we did before. So at 10 dBm, they're asking for this power level. What is this? That's what they're asking, right? So the gap here is 10 to 13 is 3, and that has a gradient of 3. That means this gap would be 9. So you always have to reference at this point, because this is the common point for both the curves, right? That's the trick. So here it's 33 dBm, and then you come down 9 down, which is 24, right? So your output power is your IM3 power is 24 dBm. Clear? Questions? That's 24 dBm. Okay. Then T. Find IM3 power level when P out is 25 dBm. So P out, so we're asking, so at 25, that's 25 dBm. What is your IM3? So at this output power, what is your IM3? That's what they're asking. Which means they're asking, what is this point? So maybe I will draw this again. That's 20. And then we found this is 33. So they're asking at 25. What is this level? So at 25, what is your input level? 5 dBm, right? Because that has to be 25 minus 20, which is 5 dBm. So that's 5, right? So that's 5, and what is this? It's 13, right? That means this gap here is 13 minus 5, which is 8. Which is this gap, same gap, right? And that's 8. So the gradient of that is 3. Okay? So if that's 3, so this has to be 24. Okay? If that's 24, this is 33, right? 33 minus 24 is this power level, because this is just a gap. Is that clear? Or not clear? Sorry, how can we have the grade? Yeah, so the gradient of this IMD curves is given as 3. It's always 3. Yeah, because that's the third order intermode.
So the third mode from delay for
Yeah, the fifth order. Normally you'll have third order, fifth order. So fifth order intermode will go like that. But it won't meet at the same level, it will meet at a different level. That will be always higher. Seventh order will go like that, but we don't really worry about fifth order or seventh order. Right? So you need to remember this gradient is always 3. That's your learning out of this. Right? That's given. So that's 24. 33 minus 24 is 9. So that's 9 dBm, right?
How come it's become 24?
This gap? Okay, so now is that clear? This is 8.
Yes.
So we have a triangle of a gradient 3.
Okay, understand.
Yeah, so that's 24. Yeah. So you can also do that using this equation, but I think for me personally, I like using it graphically. It's easier because you know what you are doing. Because this, if you miss up anything, any O with I, you'll actually confuse yourself. Right? You can pretty much derive this. This is pretty much what we did. But when you do it in the exam, I want you guys to, you'll have a question like this, right? So you have to, if you want to be clear, you can make that triangle separately and show how you got it. I don't expect you to write all these equations. You're free to do it graphically. Okay? So the questions are very simple, similar to this, but you need to know what you are looking for here. Because there's a lot of triangles here, right? So you could easily get confused with this triangle and that triangle, this triangle and that triangle. This refers to your output desired signal. This refers to your third order intermode curve. And it will always have a gradient of 3. This will always have a gradient of 1. That you need to know, right? Okay, so that's pretty much the end of this lecture.